Welcome to my second video lecture on the concept of vector spaces. In this video lecture, I'm going to talk about the concept of vector subspaces, a few examples associated to this concept, and a few propositions. We saw in our last lecture that a vector space is a package of a set along with two operations, one called as the vector addition, the other called as scalar multiplication, that together satisfy 10 properties. We saw also very few examples. We saw 4 examples. One was Rn, another was, if I go in the order, it was Rx, which was a set of polynomials of all degrees with coefficients taken from the set of real numbers. Another was a set of all m cross n matrices with real entries. And the last one that we saw was the set of all functions from the set x to r. Okay, let's take this for example. What would we get if you take n is equal to 2? We know that we will get an xy plane. What will happen if you take n is equal to 1? We know that n is equal to 1 will give me simply r1, which is simply r, which is simply the real line that you see here. So what do we see here? We know that this is a vector space. We know that this, which is r2, is also a vector space. So we see that there is a vector space lying inside another vector space. This is called as a vector subspace. So what do you mean by a vector subspace? It is a vector space within a vector space. Let's look at the formal definition of the vector subspace. So a vector subspace of a vector space. So let's begin with a vector space. So let V be any vector space over the set of real numbers. Let W be any subset of V. You say that W is a vector subspace of V if 3 properties are satisfied. Property number 1 is that W should be non-empty. Property number 2 is that this W should be closed under vector addition. What would that mean? It would simply mean that whenever you take 2 vectors from W, it should belong to W. And this should happen for any 2 vectors from W. So remember, we want our W to be a vector space lying inside the bigger vector space that is V. So this W should satisfy the first property of the vector space. That was the closure property. And this is the closure property. But if you recall, there were actually 2 closure properties. One was related to the vector addition and another was related to scalar multiplication. So what was the closure property for scalar multiplication? It said that whenever you take any vector from W, whenever you take any scalar from the set of real numbers, you take the scalar multiple of this W, it will always belong to W. What would this mean? This means that you take any vector from W, you stretch it by any quantity, by any scaling factor, the resulting vector will also belong to the space W. Also, when it comes to the closure property for vector addition, you take any two vectors, the sum of the two vectors will never ever leave the space W. Okay, let's look at a few examples now. Okay, I will start with the first vector space that we saw in our last video lecture, that was Rn. Let's take n is equal to 2. We know that n is equal to 2 will give us the xy plane. Let's call this as the x1 axis. Let's call this as the x2 axis. The vertical axis is the x2 axis. We already saw that this horizontal line turns out to be a vector space lying inside this bigger vector space, that is R2. But what about this vertical line? Why can't that be a vector subspace? So the answer is yes, it is a vector subspace. Even x2 can be considered as R1. Even for that matter, you consider any line passing through the origin, it can be considered as a vector subspace of R2. So as an example, we have the first one as any line passing through the origin. But what would happen if the line does not pass through the origin? So if you consider a line something like this, say I'll call it as L1, why wouldn't that be a vector space or a vector subspace? So we saw that one of the properties for a vector space is the existence of the very special vector called as a zero vector. So of course, if you take a line that does not pass through the origin, it will not contain the zero vector, and hence it cannot be qualified as a vector space, and hence it cannot be qualified as a vector subspace. So always remember that any set that does not contain this very special vector will never be a vector subspace or a vector space. Anyways, let's move on to our next example. So we saw that any line passing through the origin is a vector subspace of R2. Can we think of any other example? Okay, I'll tell you, other than the lines passing through the origin, there are two trivial examples of vector subspaces. Trivial means obvious, and these two examples are the singleton set containing 0 and the entire space R2. So there are only three types of vector subspaces for R2, and that is the zero space, the entire space, and something that stands between them are the line. Any line passing through the origin. So even though there are three types, we have infinitely many examples of vector subspaces of R2. Okay, but what if we have R3? This is n is equal to 3. So when you have R3, we have the x1, x2, x3, which is the three-dimensional space. So again, the same example can be taken into consideration. Any line passing through the origin. can be considered as a vector subspace. So any line passing through the origin can be considered as a vector subspace. The question is, are there other examples? Of course, the trivial examples still hold here, the 0 space and the entire R3 space. But the question is there any other example? Because here we have n is equal to 3, so we have a broader picture, so we can think of more examples. Okay, so the other examples are planes passing through the origin. So take another color. So you can have a plane that passes through the origin as another example. Of course, the plane stretches to infinity, and remember, you have to consider the sets only passing through the origin. So we have 4 different types here. One is any line passing through the origin. The second one was the 0 space. The third is the entire space, and the fourth one is any plane passing through the origin. Now a natural question arises: why do we only consider lines passing through the origin or planes passing through the origin? What if we consider, say for example, a square, say with vertices 1, 1, minus 1, 1, minus 1, minus 1, and 1, minus 1. Let's consider the square. What's so bad about this? The bad thing about this is that it does not satisfy. Of course, it has the origin, but it does not satisfy all the 3 properties of the vector subspace. Recall, the first property was that the set should be non-empty. Of course, this is non-empty. It has infinitely many elements. The second property was that the sum of 2 vectors should belong to W for every vector W1 and W2 taken from W. And the third one was any scalar multiple of any vector from W should belong to W for every alpha belonging to R and for every W belonging to W. Does this really happen? Also, does this really happen? Okay, let's take this for example. Let's take the vector 1, 1. Let's take W is equal to 1, 1. Let's take alpha is equal to 2. And what is alpha times W? It is 2 times 1, 1, and it is 2, 2. And the vector 2, 2 lies very much beyond the scope of W. This is W, and our vector 2, 2 lies over here. So you see that this box cannot accommodate all the scalar multiples. Even for that matter, if we had taken, instead of a box, say we were dealing with lines, let's take a curved line, let's take a parabola that passes through the origin. Let's take y is equal to x square. Even this will not contain all the scalar multiples, because say if you take, say this vector for example, suppose this is 1, 1. Of course 1, 1 lies in this parabola. If I take 2 times 1, 1, it will become 2, 2, and this 2, 2 will lie very much outside the parabola. And this is true because 2 cannot be written as this 2 cannot be written as the square of this 2. Okay, so the only examples that we can have for R2 for vector subspaces are, of course, the trivial ones and the lines passing through the origin. And for R3 we can have, of course, the trivial examples, any line and plane passing through the origin. Okay, now let's talk about Rx, the set of all polynomials. This contains polynomials of all degrees. But what if we restrict the degrees of the polynomials? Let's give a notation Pnx for the set of all polynomials with degree maximum n. Remember, the n is fixed here, and the ai's belong to the set of real numbers. So this will contain the 0 vector, the number 0, which will be the 0 polynomial. It will contain all constants. It will contain all 1 degree polynomial. It will contain all 3 degree polynomials, and the maximum will be the nth degree polynomials. So as we know that if you add any two, say for example, if you add any two degree polynomials, you will get another polynomial whose degree will be maximum 2. It could be 1, it could be 0 also, but it will never go beyond 2. So this is another example of a subspace, vector subspace. So for Rx as a vector subspace, you have countably infinite examples, that is Pnx, for any natural number. Even for that matter, 0 can be considered. For the third example that we had dealt with, that was M cross nr, which was a set of all matrices. Here also, as one example, we can have the space or the set of all upper triangular matrices, because we know that this upper triangular matrices can be considered only if your m is equal to n. So in particular, we'll have to talk about m n cross n r, as I said, which can also be written as m n r. So we can have the set of all upper triangular matrices as one example of a vector subspace. Even for that matter, set of all lower triangular matrices as a subspace, and we can have all set of all diagonal matrices as a subspace. We can have set of all symmetric matrices and also skew symmetric matrices as a subspace. It is very easy to check that these sets form vector subspaces of this vector subspace MNR, because when you add any two upper triangular matrices, you will again get an upper triangular matrix. You scalar multiply any upper triangular matrix with any scalar taken from the set of real numbers, you will again land up having an upper triangular matrix. The same thing happens for a lower triangular, diagonal matrices, symmetric matrices, and skew symmetric matrices. The fourth example that we had dealt with was the set of all functions, the set of all real valued functions defined on the domain X. A very good example of a vector subspace for this would be CXR. It's a very famous example. The CXR is the set of all continuous functions f from X to R. Here also it's very easy to check that whenever you take any two functions f and g from this space CXR, it will mean that f is continuous, g is also continuous, and f plus g also turns out to be continuous. Also, if you take any f and if you take alpha f, this function also turns out to be a continuous function. Even for that matter, you can take the set of all differentiable functions from X to R. We can still say that this space is a vector subspace of fxr. Let us now look at a few propositions associated to the concept of vector subspaces. As we saw that a vector subspace is nothing but another vector space lying inside a bigger vector space, which satisfy three properties. It should be non-empty, and whenever you take any two vectors, it should belong to W. The scalar multiples should also belong to W. All possible scalar multiples should belong to W. Okay. So the first proposition is that W, say for example, if you have a non-empty subset of a vector space, then W is a vector subspace of V if and only if alpha times W1 plus beta times W2 belongs to W for every alpha and beta belonging to R, and for every W1 and W2 belonging to W. This is nothing new, because we already it's basically a combination of these two properties. They're just fused. Instead of W1, as we already saw, that all scalar multiples of all vectors of W lie in W. So this can be put into this. The scalar multiple can be fit into this, and it can be called as, you will get something like this. This thing can be accommodated into this with the help of some other scalar, and you will get something like this. So this new thing is called as a linear combination of W1 and W2. So what we are trying to say here is that a subset, a non-empty subset of a vector space is a vector subspace if and only if every linear combination of vectors in W will belong to W. This is one thing. Another very important proposition is that whenever you have two subspaces, of a vector space, let's take the example of R2. We saw that any line passing through the origin was a vector subspace. Let's call this as W1. Let's take another line. Let's call this as W2. What do you see as the intersection? Intersection is simply the origin, and we know that the origin is also a vector subspace. So what I'm trying to say here is that whenever you have two vector subspaces, you can create another vector subspace out of it just by taking the intersection. So what we are saying here is that the second proposition is that if W1 and W2 are any two vector subspaces of a vector space V, then their intersection is also a vector subspace of V. The third proposition is that we can go further. If you have many such vector subspaces, and don't stop at W1, if you have many such vector subspaces, then all their intersection will also be a vector subspace, and you can write it as is a vector subspace. So you can write it as I running from 1 to infinity, Wi is also a vector subspace. But another question arises. If W1 and W2 is a vector subspace of a vector space V, can W1 union W2 be a vector subspace? And the answer is no. Let's take, for example, again our favorite example was R2. Let's take our V to be R2. Let's take our W1 to be the x-axis. Let's take our W2 to be the y-axis. So when you take the union W1 union W2, it's nothing but the cross that you see. Let's take some vector from W1. Let's take this vector, say 1, 0 from W1. Let's take this vector from W2, that is 0, 1. As we see that 1, 0 belongs to W1, and W1 is a subset of W1 union W2, so 1, 0 belongs to this union. Even for that matter, 0, 1 belongs to this union. So you have two vectors, let's call them as W1 and W2, belonging to the union of these two vector subspaces. My question is, what is W1 plus W2? As you can see that when you add this W1 and W2, what you get is 1 plus 0, 0 plus 1, which is 1, 1. And 1, 1 is this vector. And 1, 1 jumps out of the space W1 union W2. And hence, this does not belong to the space W1 union W2. This violates the second property of a vector subspace, and hence W1 union W2 cannot be a vector subspace always. But yes, again the question arises, under what conditions can W1 union W2 be a vector subspace? So W1 union W2, okay, to start with we will need two subspaces. So if you have two subspaces, another vector space, then W1 union W2 can be a vector subspace of V if and only if either this W1 is sitting inside W2 or W2 is sitting inside W1. So we know that if W1 is sitting inside W2, then their union would be simply W2. If W2 is sitting inside W1, then their union would be simply W1. And we already saw that they are vector subspaces. And hence, one side is obvious. The other side is a little tricky.